So hello everyone, I'm Norman Wildberger. We're at the University of New South Wales. And today we're going to look at some applications of curvature to turning numbers and winding numbers of curves, also sometimes called the index of a curve. And we're going to make an important shift today, sort of in terms of our orientation. So we're going to start introducing integrals, square roots, possibly some transcendental functions, infinite sums, irrational numbers, and so on. And so many of you will know that I don't entirely approve of the current treatment of these things. So I need to say a little bit about how we're going to orient ourselves towards these things. So up till now we've been taking a very algebraic point of view towards the subject, and today we want to extend ourselves. So what we're really going to do here is, the way we're going to think about it, is that we're going to introduce ourselves to applied mathematics. So I think it's very difficult to formulate these things completely correctly in the framework of pure mathematics. But it is possible to talk about them meaningfully in the context of applied mathematics, where we're thinking about approximations, making statements which are approximately true but not necessarily completely true. All right, so the key thing is that we're willing to work with approximations. And in fact, we interpret our statements in terms of approximations. And in fact, this is exactly what happens when you actually do these calculations in real life. So the engineer, the physicist, the chemist, the computer scientist that is working with these kinds of things inevitably is actually working with them effectively at the order of decimal approximations. So the infinite decimals or infinite processes that the pure mathematician likes to talk about are in practice replaced with finite processes and finite decimal approximations. And our point of view is that that's actually the most reasonable framework in which to think about all of these things. That we don't actually need this la-la land idea of these ideal things that are happening way beyond our view. We can just work with approximations in the same spirit as an engineer or a physicist or a computer scientist. Okay, so let me illustrate that idea with the idea of arc length of a curve, which is a very natural, important concept in differential geometry. So suppose we have a curve, let's call it gamma, and we're interested in its length, the length of this curve. So what is the meaning of that? Well, I remind you, the usual formula for it is perhaps something like we're integrating over gamma ds, okay, where ds is like an infinitesimal arc length, sometimes written as square root of dx squared plus dy squared. So if we have a particular curve gamma, how do we actually compute this integral? Well, there are several stages. The first thing that we do is we partition the curve into a number of pieces by finding a sequence of points more or less equally spaced, but they don't actually have to be completely equally spaced, along the curve. All right? So that's really the step one, is to partition the curve. Now before we go further, let's observe that this in fact is sometimes quite problematic. If our curve is given in terms of a parameterization, then it's not too hard to partition it. However, if it's an algebraic curve that may not have a parameterization, it's maybe very problematic even finding points on the curve. What we can do is we can use essentially Newton's method to find points which are approximately on the curve. That's actually in practice what we can do. We can get our computers to take a given curve and to find points which are close to being on that curve or satisfying the equation. And how much work we put into that computer program, how long we let it run, will determine sort of how close these points are to satisfying whatever equation we have of the curve. So already at this stage of partitioning gamma, there's a little bit of approximation involved. All right, what's the second step that we do? Well, we look at all these various line segments and we compute their lengths. Right? So step 2 would be we compute, well, let's call these points something, say P0, P1, P2, up to say Pn. So what we do is we compute these various distances, say from Pi to Pi plus 1. Okay, and that's given by some formula involving a square root. So xi minus xi plus 1 squared plus yi minus yi plus 1 squared. So we have to compute a square root in order to get a length. Well, as I point out in my Math Foundation series, calculating square roots is again something that we can only do approximately. Okay. So you want to find the square root or the length between 2 points. It's a computer program, it's a process that allows you to spit out more and more decimals of whatever square root we're interested in. And that, how far we want to go in that process is up to us in terms of how much patience and computer time we have. But it's a little bit illusory in my view to say, well, we're just going to keep going forever and compute the entire square root. That actually takes an infinite amount of time. It's actually not possible to do that. And it's not really necessary for us to pretend that we can do it. Currently, we pretend that we can do what we can't actually do and hope that nobody calls us on it. We're all bluffing. All right? But I'm saying we don't need to bluff. We can just be honest and say, well, this is a potentially infinite process that we can only go a finite number of steps towards in any actual real situation. Okay, so that's the second point where we're doing something that involves approximations. And of course, then we have to actually add these up and form the sum from I equals 0 to n minus 1 of these various distances. Okay. And then the third step is we have to take a limit of this sum as n goes to infinity. Of this sum that we've just computed. Okay, that's another infinite process that involves, again, an infinite number of steps, which we, in fact, typically cannot do in complete practice. So, the pure mathematician, these days, at the beginning of the 21st century, believes that all these things can be theoretically done. I believe that the policy, the view on this is going to change, and that we're going to start adopting a more realistic point of view where we acknowledge that we can't actually do this. And the issue is more of how well can we make an approximation. So it's not necessary for us to believe in irrational numbers and real numbers and infinite processes that can be completed infinitely. So the square root process is a good example to think about. If you have, during some calculation, you have to take the square root of 57. Of course, our calculator will spew this out to a certain number of decimal points for us. The algorithm to compute a square root was known since ancient times, and it's an algorithm that's very interesting to do. It's actually an algorithm that you can do by hand. And what you will find is that, well, there's a certain process that you go through. I guess the first one will be 7. You can compute these decimal digits one at a time by a certain well-known process that's essentially thousands of years old. But what you will find when you're doing that is that the process gets harder and harder and slower because the numbers involved, the arithmetic that you have to do is more and more complicated, dealing with larger and larger numbers. So the difficulty of the task goes up like this. It becomes a mountain. Right? You can spend half an hour and get 10 decimal places, or you can spend 2 days and maybe you can get 100 decimal places. But how far up this mountain you want to go depends on your patience. and the power of the computers that you have helping you. And now our current understanding, and the understanding of most undergraduates, is that, well, we can just invoke this infinite process that does all of them at once. So we can pretend that there's a sort of a top to this mountain. And we can just proclaim that, well, we just go up the mountain until we get to the top. We have various jingoistic words that we use this. We say, well, in the limit, we get something or other. But in fact, there is no limit. You can just keep on going and keep on going as much as you have patience, and then you have to come back down and report on what you've got. This is a mountain that does not have a top, okay? It just keeps going up and up and up, steeper and steeper and steeper. Now, the current theory towards real numbers is to say, well, yes, that may be true, Norman, but what we can do is we can create a top. We can create a top by essentially defining the real number, the irrational number, which is on top of here, in terms of the actual sequence itself. We can create these new numbers from the sequences, from the algorithms, and then proclaim that those numbers are the legitimate conclusions to our calculations. It's very self-referential. And it means that in practice, the arithmetic of real numbers is largely vacuous. Okay? If I ask you for real numbers, you'll say, okay, but root 2 is a real number, and pi is a real number, and e is a real number, and so on. And if I actually ask you to define what those things are precisely, it's a little bit more problematic. Yeah?
And you said we assume that it exists, but isn't that like an axiom sort of thing, like the least upper bound axiom of real numbers? Doesn't that come from that?
Okay, so the question is, doesn't the existence of real numbers sort of follow from some axiomatic treatment?
What I'm saying is, like, I don't think pure mathematicians would say that is true. They just say, if it's true, then that's the limit.
Well, pure mathematicians say different things on different times. So there's various ways of ostensibly creating the real numbers. So there's a theory of so-called Cauchy sequences of rational numbers. There's a theory of Dedekind cuts. There's a theory of continued fractions. There's a theory of just applying things with infinite decimals. None of those really work very well when you look at them carefully. So mathematicians sometimes retreat to an axiomatic position, which is the one that you're referring to. And they say, okay, maybe we don't know how to do this. Why don't we just assume that we can do it? Let's call it an axiom.
But they don't assume that you can do it. They say, if we can do it, then that's what the answer is.
They may say that they're doing that, but in fact they actually do assume that they do it. In your theorems, the theorems do not start out by saying, if our axioms of real numbers are true, then the following works.
That's implicit.
It's only implicit in certain frameworks. It depends on which school of thought you're coming from. Okay, so to illustrate that sort of the essential vacuousness of real number arithmetic, let's just talk about how does one actually add real numbers or multiply them. And if I asked you, how do you add 1/2 plus 1/3, you'd all know that there's some work that has to be done, and you have to do that work, and then you get an answer. If I ask you, well, what is root 2 plus pi? Please make that calculation. You know what root 2 is, you know what pi is ostensibly, so calculate for me root 2 plus pi. Well, you'll probably think, well, geez, root 2 plus pi. And after a while, you'll say, well, that's just root 2 plus pi. That's the answer to the question. Let's ask a little bit more challenging question. Let's take root 2 times e. Let's make that calculation with real numbers. Okay, let's think. What's root 2 times e? Root 2 times e. I know what it is. Do you all know what it is? It's root 2e. And finally, one more calculation. Let's calculate pi to the e. What do you think that might be? Here's an infinite decimal or an infinite real number. Here's another one. We have to calculate 1 to another power. How are we going to make that calculation? You all know the answer. You just write down pi to the e. It's very hard to come up with examples of real number arithmetic that illustrate that you actually understand something that's beyond the rational numbers. Okay, so our point of view is that real numbers currently don't exist. Maybe tomorrow someone will figure out a theory of real numbers and write it down. Maybe someday calculus texts will, in their first chapter, lay out a proper theory of real numbers. Currently, that's not done. There is no proper theory of real numbers, so we're going to avoid them. And we're going to think about things from an applied mathematics point of view. So when I write down square root of 2, I just mean 1.414 blah, 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 to maybe 10 decimal places, or maybe 20 decimal places. It's a rational number which is approximately, has the property that its square is 2. Okay? And all our statements involving integrals, infinite sums, transcendental functions will be interpreted in that way. Okay? We're making statements about rational numbers, but they are approximate statements in the context of rational numbers. Yes?
If the square root of 2 is actually an approximation, and then you take the square of the approximation, do you get back to exactly 2?
No, and so there's an element of approximation or error in all of these statements. All our statements are true up to a certain amount of error. And the amount of error depends on, well, how much work we've put in to make calculations which are accurate or not. How many decimals we're carrying along. In fact, this is nothing really more than what an engineer does in practice. An engineer doesn't need this complicated theory of irrational numbers. They just work with finite decimals as approximately good enough, and they just ignore all those trillions of digits that carry on supposedly after the 10th one. All right, so this is roughly the approach that I'm going to take, so I just want to point that out so that those of you who are following the Math Foundations series will not accuse me of inconsistency. All right, so I will explain this point of view at much greater length in my Math Foundations series. Now let's have a look at some applications of curvature to curves. All right, so let's suppose we have a curve, and at some point here we have the center of curvature, so that there's a circle through here which approximates our given curve at that point. Then if this circle's radius is r, then we know that the curvature is 1 over r. And if we're interested in approximating this curve with a part of the circle, then we have a very nice relation in the circle that we can use, which relates the arc length, which we'll call ds, to this angle, which we'll call d theta. Okay? So in a circle, of course, the relationship is that ds equals r times d theta. And since that's true for a circle, and the circle is approximating our curve to quadratic order, we can think about this as being valid for our curve as well. In other words, if we have a small change in angle, then we can give an approximation for the change in arc length of the curve. We can rewrite this formula by just inverting it and writing it as d theta equals 1 over r times ds, which is k times ds. And so that means that if we integrate, let's say from the position A to the position B, if we integrate along the curve, maybe I'll write like this, so along the curve from A to B, and if we integrate k ds, then what we're really integrating is the same as the change in the angle, where the angle is really now a normal angle. So this angle theta can also be interpreted as the difference between that normal and that normal. So if we look at the curve and we consider all kinds of normals to it, it's often nice to talk about a unit normal. Then over here we can graph the unit normals by placing them all on a single circle of radius 1. So for example, if this is the point C, and that's the point D, and that's the point E, and that's the point F and G, and so on, then we can position those various normals on this circle. So that would be at position C, that would be at position D, and then E a little while later would be up there, and then F a little while later would be there. So I want you to think about the normal to this curve. Okay? As we go along the curve, the normal is moving around. And we can think about over here, correspondingly, the normal rotating around a circle of radius 1. And what we're saying with this relationship here is that we go from D to E. The angle here is d theta, then that means that the angle between these two normals is also d theta. So that would be between D and E, let's say. That d theta there is exactly the same as that d theta there. So this integral, the integral of the curvature against the arc length, can be rewritten as really what we're doing is we're integrating the change in theta as we're moving along the curve from A to, say, B. Let's draw those as well. So there was A, and there was B. So this is going to be, overall, it's going to be the angle at B minus the angle at A. It's just the change in angle or orientation of the unit normal. All right, so as an interesting consequence of that, if we have a closed curve, say one that looks like this, gamma, and we think about what happens to the unit normal as we go around. And over here is our reference circle where we just have the unit normals. Let's start, for example, perhaps at this point here, and we're going to go around and come back to that point. So at the starting point, let's call it A. Our unit normal is in this direction. And as we go around the curve, let's see if we can do this. So if we go around the curve, here I'm going to follow the normal. So once I'm at this point, the normal will be there, and then it'll be here. And then as I moved up there, it'll have gone backwards a little bit. And then up here, and then at this point it'll be here, and then over here, and then over here, and then it'll go backwards a little bit, and then here, here, and back to where we started. So it's made this sort of circuitous route, but it's altogether managed to go around altogether once. And so the total change in angle, in this case, the change in theta after one revolution, after one, let's say, turn, is 2 pi. So in other words, we can say that the integral around the curve of k, the curvature times the arc length, ds, is going to be, in this case, 2 pi. But there's a few things that I have to mention here, sort of some caveats, okay, to make this work. To make this work, what we have to do is we have to recognize that it's not really curvature so much as signed curvature that we require here to make this work. Okay? So this really requires thinking about signed curvature, which is just like the ordinary curvature, except that it might be plus or it might be minus. Why? Well, because as we go along the curve, say here, this one here, here the center of curvature is on this side. At some point there's a point of inflection where the center of curvature essentially goes off to infinity. And then a little while later it comes in from the other side, and over here the center of curvature will be something like this. So what we have to do is we have to treat the curvature on this side as different from this one. Right? Because the actual changes in the normal are going negatively in this direction while they're going positively in this direction. If we assume that we have the usual positive orientation, that this represents a positive direction. So if we have something a little bit more complicated, like something like this, well, in that case, what's happening to the tangent? Start at some point. There's our tangent. And if you just follow the normal, so there's the normal, rather. If we follow this normal all the way around, and you just sort of watch what its orientation is. At this point here, it's gone around once in the positive sense. And then as we carry on, well, it's just going around a second time. So altogether, it's made 2 circuits around the reference circle. So here the total curvature is two times 2 pi, or 4 pi. But it's still the integral of k radius. So as another example, if we look at the lemniscate and consider what happens to the normal. So if you watch the direction of this normal, okay, it's going around like this. It's on its way to have made a complete turn, but now it's coming back. And in fact, now it's back to where it started. So this is a situation where the normal has done something like this. And the total amount of turning of the normal is 0. The total change in the orientation of the normal is 0. So here the total curvature is 0. Okay, there's an interesting connection to this business with a discrete form of curvature that's important for planar geometry and polygons. So the discrete curvature is really very close to the classical formulas for the sum of angles in a polygon. And to make that a little bit easier, I like to think in terms of a more natural normalization of angles. So, of course, you all know that there are different schemes for measuring angles. Okay, so in one scheme this is 90 degrees, and in another scheme it's pi on 4, And in the European scheme, I think there's 100 grads. Okay, but these are all rather a little bit arbitrary or complicated. There's a more rational approach to how much turning there is going on here. So that's what I call a turn angle, tau. In this case, the turn angle would be 1/4. So the basic reference is that we're thinking about once all the way around is a turn of 1. Okay, so all the way around, is a turn of tau equals 1. That's the natural unit in this story. Right? It's a situation where there's a natural unit. The natural unit is all the way around. That's 1. Okay? It's artificial to introduce 90 or 360 or anything else really. It's 1. 1 turn all the way around. So in that case, this would be a turn of a half. While this would be a turn of -1/4. Well, we'll adopt the usual convention that this is still our positive direction. Was there a question?
Do you mean pi on 2 or not pi on 4?
Pi on 2. Thank you. That's right. Okay, so with rational turn angles, some formulas are a little bit nicer. So for example, suppose we have a triangle, and I'm going to use this notation for turn angle, so that'll be tau 1, tau 2, I'll make them all go in the positive direction, tau 3. Okay. So if we want to add up these turn angles, one way of doing it is to think of the complementary turn angles. Let's call them mu1 and mu2 and mu3. All right. So with this framework, tau 1 plus mu1 equals a half, because 180 degrees is the same as a half turn. Then tau 2 plus mu2 is a half. Tau 3 plus mu3 equals a half. But the sum of the mu's is easily seen. If we start here and we take this mu1, and then we add this mu2, and then we add this mu3, we're back to where we started. So mu1 plus mu2 plus mu3 equals 1. And then if we combine these equations with this one here, we can conclude that tau 1 plus tau 2 plus tau 3 equals, sum of those 3 is 3 halves, and we subtract 1, we get 1/2. So that's familiar enough for triangles, but if we have a polygon with n vertices, we can do the same thing. So an n-gon, we may have a tau 1 turn there, a tau 2 turn there, all the way up to a tau n turn there. And now instead of doing the tangential things, let me do something that's a little bit more normal oriented, a little bit more in keeping with the thinking of in our course. Let's look at normals instead. Oh, normals were red, so let me do it in red. So there's a normal there, and there's a normal there. So these are normals. And there's a normal and another normal. Okay, and let's observe that these turns in between here, let's call them mu2, mu1, and so on, all the way up to mu n. Then we have the same kinds of relations that tau 1 plus mu 1 equals. So what's this tau 1 plus this mu 1? Well, here we have 90 degrees, which is now called turn of 1/4. And here's another turn of 1/4. So these two add up to a turn of a half. All the way around we've agreed is a turn of 1. So this tau 1 and this mu 1 still add up to a half. 180 degrees if you prefer. Okay. So but in terms of turn angles, tau 1 plus mu 1 equals a half, and that of course is the same for all of them. And now if we think what happens to the sum of the mu's, the sum of these external normal turns, we'll have a look at the normal. We'll start here. Okay, so the normal here is the same as the normal there. So the first, okay, let's start here actually. We'll start here, and then the first thing we do is we have a turn of mu 1. And then going here, we're not doing anything, and then we have a turn of mu 2. And then over here, a turn of mu 3. All the way up to, and eventually we get here, a turn of mu n. And we're back to where we started. So in this kind of situation, the sum of the mu's is 1. Just as it was for the triangle over there. And from that we can conclude that tau 1 plus all the way up to tau n, the sum of the internal turn angles is, well, we just add up all of these and subtract 1, which is the sum of the mu's. The sum of all these will be n over 2, and then we have to subtract the sum of the mu's, which is 1. So these are just versions of calculations that are probably familiar to you from high school, but here we're stripping the theory from angles like with degrees or with pies. The essential feature is really just the amount of turns. That's the natural unit when we're talking about going around a circle. Okay, there's of course variance on this. Variance concerned when the polygon is not necessarily topologically like a circle. So here this polygon was more or less a convex polygon. So this works for a convex polygon, but we can apply the same kind of thing to non-convex polygons too. So for example, if we have something like this, maybe we'll give this to you as a problem. Calculate the sum of the internal turn angles. I might just write T angles or tangles. All right, so if we have, there's a natural connection now between the continuous case and the discrete case, because a continuous curve can be approximated by a polygon. And then our formulas for continuous curvature connect with formulas for these turn angles. So to make sense of that, we'll go back to this formula that the change in theta equals the integral of k ds along some curve. So if we're interested in the change in the turn angle is just the ordinary angle divided by 2 pi. So we get d tau equals 1 over 2 pi integral over gamma k ds. which maybe has a sort of a familiar ring for those of you who have done some complex analysis. So if we have a general curve or a general polygon, we can do the following. So we can define the index or turning number of a curve. So what this is the tau of a curve is, by definition, the number of times the normal, say a unit normal, just to be precise, a unit normal turns as we go once around the curve. So here's a curve. Let's choose an orientation because we need an orientation. Let's say there. So we're going to go this way. So what we're going to do is we're going to look at a normal. We could also look at a tangent. That would be exactly the same thing. So the difference between a normal and a tangent is only a quarter turn, which is maintained consistently throughout. But let's look at a normal because it's sort of more in keeping with the differential geometry story. So we'll start with a point, say right there, and we'll choose this direction here. So let's start with a sort of outer normal, which in this case means that the normal's on the right-hand side as we're going along our curve. Okay, so have a look at this normal and see how many times it goes around as we go around the curve. Okay. So when I'm saying going around, I'm thinking that you have to actually translate this normal to some fixed position and watch it going around on its own little circle. Okay. All right, so here it is right here, and it's moving around. Okay, so here it's going this. At this stage, it's gone around half a turn, right? From where it started. And then over here, and now it's back to where we started. It's gone around a one full turn. Okay, so one so far. Okay, now it looks like it's going up, but now it's back to where it was just a minute ago. And now, actually now it's reversed what it did before. Now it's back to where it started, right at the beginning. Okay, now it's going in this direction, coming back over here. Now it's back to where it started, but it's gone around once. So altogether, how many times has the tangent gone around? And has it gone around a positive number of times, or has it gone around a negative number of times? It's gone around a total of 2 times, right? Once, twice. So in this particular example, the turning number, or the index of this curve, is 2. Now there's a kind of an easier way of calculating this thing instead of doing what I just did. What you do is you choose a fixed direction, let's say this one here for the sake of argument, and you just ask yourself, when does the curve have this fixed direction as a normal? So that'll be right here, and then also right here. Let's see other places where there's right here. Right here there's such a direction. Right here. Any other places? How about over here? Also here. Let me better check this. Oh, so no, this was not one. here the actual normal was in this direction. Okay, so because we've chosen our normal so that it's on the right-hand side as we're going down the curve. All right, so we're going down the curve here. It's on the right-hand side, on the right-hand side. So here's on the right-hand side, so it's there, yeah. And over here it will also be in such a direction. There. There. Okay, so I think I found these positions right here, right here, 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 and here. And each one of these places is a place where the normal is crossing this fixed reference point. But I'm now going to determine for each one of these whether it crosses it in this direction, which I'm going to deem the positive direction, or whether it crosses it in this direction, which I deem the negative direction. Okay. So here, for this one, what's it doing? It's going like this. So it's crossing, it's going in this direction, so it's going positively. When we go over here, it's the same story. It's going positively over here. When we're over here, with this one here, well, at this point here, it's down like this, and then it's here, it's here. It's actually going in the negative direction for that one. And then for this one here, it's here, and then here. That's another positive. And finally, for this one here, started over here and then it went like this, so it's going in the negative direction through that one. So if we're watching the image over on this side, every time there's a positive, it means that the vector is going through in this direction, and every time it's a negative, it'd be going through this direction. So if we had a friend who was just watching here, he would say, well, the tangent normal has passed in this direction altogether 1, 2, 3, 1, 2, 3. Oh, I didn't do this one here. That's also a positive one. 4 times. It's gone this way 4 times, and it's gone this way 2 times. For a total of 2 times total in the positive direction overall. Okay, so next time we'll have talk a little bit more about index turning numbers and also talk about winding numbers, also important in complex analysis. See you then.